Hello everyone, welcome to the day 1 of week 4 of this course. So in the last week we looked at the matrix representations of various symmetry operations, and on your screen you can see all the matrix representations that we formed for different symmetry operations. For example, identity, different sigma planes, proper rotation and improper rotation, as well as inversion symmetry operations. In order to form these representations, we chose x, y and z coordinates of the Cartesian coordinate system. So x, y, z acted as the basis set for forming these representations. Okay. So you can look at all these representations that we formed in the last class. Now after we formed these representations, we can cross check whether these representations are capable of acting just like the symmetry operations themselves. So we used x, y, z as the basis functions. So if we form a column vector by taking this x, y and z and then operate this matrices on that, we will find what will be the outcome. Okay, so we can verify whether these matrix representations are giving back the same modifications of this x, y, z column vector as that would be given by the symmetry operators itself. So for that, if we look at the screen, so this one is identity matrix, which represents the identity operation. So when it operates on the x, y, z column vector, it gives back x, y, z column vector itself. So it retains its property. Okay. So if we look at other symmetry operators and their matrix representation and then operate on this x, y, z coordinates, we will find out whether really all of these matrix representations they work parallel to these symmetry operators. So here this matrix corresponds to the inversion operator. So when it operates on this x, y, z column vector, we get a column vector for which all x, y and z coordinates, they are inverted, that is they have minus signs, so which is the signature of the inversion operation. So if you verify all of them, you can figure out that truly these matrix representations are capable of functioning just like the symmetry operators themselves. So they are adequate representation for these operators, symmetry operators. Now after we learn how to form these representations for the symmetry operators, now we are in a condition to form the representation of a group. So what is the definition of a group representation? So a representation of a group is defined as follows. So this representation of a group is the set of matrices each corresponding to a single operation in the group that can be combined among themselves in a manner parallel to the way in which group elements, that is the symmetry operations here, they combine, right? So we already stated that this matrices that we found for each symmetry operators, they truly act like the symmetry operators. So they retain all the properties of any symmetry operation. For example, when you operate on any particular function, it acts exactly like the symmetry operator. Moreover, when we combine two such matrices which represents two symmetry operations, the resultant matrix is a representation for the symmetry operator that would have that we could find upon the combination of the original two symmetry operators. So we can cross check that. We can work out a particular case of C2V point group. So in this case, we will consider that the principal axis of rotation that coincides with the z axis in the of the Cartesian coordinate system, and the sigma v plane, C2V has two sigma planes and both are vertical planes. Now we differentiate them as sigma v prime. So here we choose sigma v to be the xz plane in the coordinate system and sigma v prime to be the yz plane. Now, you know, after considering this, we can get the matrices as follows. So this is for the identity, this is for C2 rotation axis, sigma v and sigma v prime. Okay. So now we have to cross check whether it really acts like the symmetry operations for the point group C2V. So now here you know, we have the group multiplication table here, so that will help us in, you know, proving our point. So if we take two symmetry operations, sigma v and C2, here C2 is C2z, and combine them, then the resultant should be sigma v prime, as I can easily find out from this group multiplication table. So sigma v C2, this combination, if I go by, you know, acting the row operation first, then sigma v and followed by C2, here it gives me sigma v prime. That's what we have here. Okay, so you can choose any other symmetry operations and combine them, and you can find the result of that combination from the group multiplication table that we have already learned. Okay, so now we take the matrix representations for this sigma v and C2z as it is written here, combine them, and we get this matrix. Now what this matrix stands for, if we just go back, we see that this corresponds to sigma v prime, right? You can find a similarity, you can find that this matrix is exactly same as what we get here. So we can see the law of this combination, it holds exactly the same way as that the symmetry operations would you know, follow. So what you can do, you can try out all other combinations and, you know, verify whatever we just said. Now once we have verified all these things, then we can say that all these matrix representations, if we use all together, we can find a representation of the group itself. So that is what is shown here. So here we have formed you know, a kind of table here, where at this top left corner we have the symbol of this point group under consideration C2V, and here you have all the symmetry operations written. Now this is our representation, this whole thing is our representation. The name of the representation that we have given here is gamma. That's normally people use for any such representation. So each matrix corresponds to each symmetry operation, and as a whole this is a representation of a group. Very fine. Now we have a genuine question here, that okay, I took XYZ as my basis set and found the matrix representations, put all of the matrix representations against the symmetry operations in a table, and we call it a representation. Now how many such representation one can find? So the clear answer is really large number of representations can be formed. It completely depends on you. You know, what basis set you choose, based on that you can find the representation. So here we took XYZ as my basis set. I could select any particular molecule. Suppose I am trying to find out the representation for the molecule water. So what I can do, I can take all the XYZ coordinates of the three atoms, 2 hydrogen and oxygen, and then we can find the matrix representation of the symmetry operations. So when we took just XYZ, we we got 3 by 3 matrices for each of the symmetry operations. For XYZ coordinates for all 3 atoms together, I should have 9 by 9 matrices. Suppose I have a molecule which has 10 atoms in it, and I choose all the XYZ coordinates of all the atoms, then my number of or the dimension of my matrix representation would be 30 by 30. Okay, so it depends in that way. So we are also not limited by this coordinate system. We can take anything. We can take any given function. For example, I can take any bond vector. I will give you a very quick example. Say I can take say this molecule. So what point group it belongs to? It belongs to D2H point group, right? So I can find various different representations for D2H. That's what we can prove. So one way I showed by XYZ. Another way I can take that for each one of these atoms I can use their coordinates. Okay, so this hydrogen atom, it will have its own coordinate, XYZ coordinate. This one will have its own XYZ coordinate. So this carbon, this hydrogen, all of them will have their YZ coordinates. So total I have 6 atoms, 6 into 3, 18 18 coordinates altogether, right? So I will get, if I use all the XYZ coordinates for all the atoms, then I will get an 18 by 18 matrices for each of the symmetry operations. But as I said, I am not limited to this XYZ coordinate system. I can choose anything, whatever I want, and which is capable of representing this molecular structure some way. So for example, I can consider this CH bond. Okay, so I can choose the CH bond vector. Okay, so I can choose this 4 bond vectors. I can put their names like 1, 2, 3 and 4, or I can write A, B, C, D. Now these 4 bond vectors I can use as my basis function, right? So my basis set will be 1, 2, 3, 4. Then what I have to do, I have to operate all the symmetry operations on this structure, on these bond vectors, and see how this bond vectors, that is how this basis set that is formed out of these bond vectors, they are getting modified. So in this particular case, my bond basis set is something like this: 1, 2, 3 and 4, and that I can represent in terms of a column vector like 1, 2, 3 and 4. And suppose I operate identity operation on this. So identity operation will have its matrix. So upon this identity operation, I will get my original column vector back, 1, 2, 3, 4. How can that be possible? If I have an identity matrix where all the diagonal elements as 1, while non-off diagonal elements are all 0. Similarly, I can find what will happen if I operate as C2. Okay, so in case of C2, 1 will go to the place of 3, 3 will come here, and this one will go here, 2 will come to this place. So I will know exactly how my column vector is getting modified after a particular operation, and then correspondingly I can find the matrix form of that symmetry operation. So this is the matrix form for the identity operation. Similarly, I can find for the C2 operation, I can find other C2 primes here, okay, which are perpendicular C2s. I can find the matrix form for the sigma H plane. We have a sigma H here. For example, if I have sigma H, what will be the matrix form? Because sigma H is not going to change any of these bond vectors, right? So it will be exactly same as this. Okay, so in that way I can find one particular representation. I can choose other things. For example, I can find I can use the orbitals, various different orbitals. Okay, say I can choose the pz orbitals of these carbons, or I can choose the s orbitals of hydrogen. I can constitute a basis set having n numbers of basis function in it, and then I can form those representations. Okay, so that's why we say that we can form a very large number of representation for any given point group. Okay, and we will see after a few classes that it's up to us that what basis function that we will choose. It will moreover depend on the problem that we are going to address. Okay, so based on that we have to choose the basis functions, and then we have to form the representations. Okay, and then we have to work with those. So some more example here. So as we said that large number of representations can be formed. So the smallest representation, representations with smallest dimension that one can have is a one-dimensional matrix, right? So I can have a one-dimensional matrix. Say for example, in this particular case, if I take this particular double bond as my basis function and operate everything, so I will get only one element there, right? So every time if I get one element, ultimately my matrix will be a one-dimensional matrix. So I will have a matrix representation like one of these. So each one of these are some matrix representations. Okay, so say here we are giving an example of C2V, right? So this is for C2V. So for example, like water. So if I just take the specific example here, instead of this large molecule, let's take a molecule like water which has a C2V point group, and so what I can do, I can take the say pz orbital here. So this pz orbital will act as my basis function, and I have only one function, so this only single function will form my basis set. Okay, so when we operate say identity on this one, what is going to happen upon our identity operation? Nothing is going to change. So that will have 1. If I operate say for example C2, it's not going to change anything, right? So C2, which is along say z axis, that will also give a matrix which has element as 1. If I operate sigma v in this way, okay, say sigma v say xz, this is say yz. Okay, so sigma v yz, this is not going to alter this pz orbital. Okay, so this plus will remain plus, minus will remain minus. Okay, so one half is just the mirror image of the other half. So this will also give a matrix having element only as 1, and sigma v xz, which is the molecular pair, that will also do the same thing. So I get a representation for which all the matrices are one-dimensional and the elements are just unity. Similarly, I can choose any other thing and find another representation. I can choose this bond vectors, say 1 and 2, and I can find representation where each of these matrices will be two-dimensional. Okay, so 2 by 2 matrices. So I can find many such representations, and say for example here I said like with XYZ for water I will get 9 by 9 matrices. Okay, and I can choose many such things. Now this particularly matrix representation, what does it do? So matrix representation, the matrix, it contains all the necessary information and all the necessary properties of all the symmetry operations. We are convinced about that. Now, after we can form the representation of the group, so that means these matrices altogether they give us certain information which are condensed in those matrix form. Now, what is more intriguing about this representation by using matrices is the trace of the matrix. So, what is the trace of the matrix? Trace of a matrix is the sum of all the diagonal elements of a square matrix. So, here this chi symbol is used for the trace of a matrix, and you can see that all the diagonal elements are summed up here. Now, in case of square matrix, this sum of this diagonal element, that is the trace, is also called the character, and there is a definite reason for calling it a character, because the matrix itself contain all the information or all the properties of the symmetry operation, but moreover this trace of this matrix, it contains all those information and properties in even more condensed form. So, instead of using the whole matrix representation, I can use just the trace of that matrix and get all the characteristics of the matrix, which in turn give me all the characteristics of the symmetry operation. Okay. So, that is why this trace of the square matrices which represent the symmetry operations are called the characters. So, we will be using these characters throughout this course henceforth, and this is very important. Now, let's see let's look at some of the characters of the of different representations that we can form. So, some of this matrix representations for sigma planes that we have already seen in our earlier part of this lecture. So, if you look at each one of this matrix, this is xy, xz, yz. Okay. So, when we sum all these diagonal elements, what we get? 1 plus 1 minus 1 equals to 1. Here again 1 minus 1 plus 1 equals to 1, and here also minus 1 plus 1 plus 1 equals to 1. So, for all this three different sigma, three different representations of three different sigma planes, sigma xy, sigma xz, sigma yz, they have the same characters. This is something which you should note. Now, again, let's look at the character of C2 representation. So, when we have this C2, the representation of C2 formed by using xyz basis set, what I get if I sum all this diagonal element, then I get the character as minus 1. Okay. Similarly, if I form a matrix for C3 operation, then I sum up all these characters and I get the character as 0. Okay, and I can find the identity and for inversion operation or SN operation. So, in this way we can find the characters. Now, we have been dealing with matrix representations so that we can come to this particular thing called trace and also character. I will very soon tell you how without even forming the matrix representation you can find out the character, because our ultimate aim is to find this character, because it is the entity which contains all the necessary information and all the necessary properties of the symmetry operations in a most condensed form. So, our aim is to get those characters. So, I can go that get those characters by forming the matrices, summing up all the diagonal elements, but also there are ways that I can get the characters directly. So, we will talk about those things later, but to begin with, I will urge you to work out the representations for different symmetry operations, not only by taking this only Cartesian coordinate system x, y, z, but also like putting Cartesian coordinate system for all the atoms, taking them altogether as the basis set and forming the representations, or in the way I showed it for say water or ethylene, using various different type of basis set and finding out the representations, and thereby finding out the characters of each of the matrix representation corresponding to each of the symmetry operations. Okay. Now, let's look at some beautiful properties of these characters. So, one most important property of this character, this trace or the character, we are going to discuss now. So, now if we look at the properties of the conjugate matrices. So, what is conjugate matrices? Let's talk about the matrices which represents the symmetry operations. Okay. So, symmetry operations, if we consider, and if I tell you, okay, these are the conjugate symmetry operation, what do you understand by that? You immediately will tell that, well, those symmetry operations which are connected by similarity transformations are conjugate symmetry operations. Okay. So, in case of matrix representations, it will also follow the same similarity transformation relations as that of the is followed by the symmetry operations themselves. So, the matrix representations correspond to the symmetry operations which are conjugate will also be conjugate here, fine. So, the an important theorem about this conjugate matrices is that their characters are equal, are identical. So, now we have learned that these conjugate elements of a group, they form a class, right. So, once we do the similarity transformation on all the elements of a group, in our case the symmetry operations, we find that, okay, certain elements are forming certain classes, okay, and what we are going to see here, that the matrices corresponding to those elements belonging to class, they give exactly same characters. Here, for example, if I have two conjugate matrices A and B corresponding to two symmetry operations, say, then A and B will have same characters, and we are going to prove that. So, what I mean here is, for example, say I have A and B are two matrices representing two symmetry operations. Okay. So, if I have a relation like okay, A, B, and if I have A, then C and D will have their characters identical. So, how do I prove that? So, if I want to find out the character of C, so that means character of say C equals to the sum of all the diagonal element of the matrix C, correct. So, if I write this as sum over J, C, J, J, those are the diagonal elements, right. So, if I break this one further, excuse me, I can write it as a product of the A and B matrices. That means the product of the elements A, J, K and A, B, K, J, right. So, A, J, K, B, K, J, I can write that. Now, what will be the character of the matrix D? I will have say the diagonal element D K K summing over K, right. So I can split them again just in the same manner. So I have sum over k and sum over j, then I can have D is B and A, right. So I will have B k j and A j k, correct. Now I can rewrite this one because the order of the summation is immaterial. So what I can do is I can write it in this fashion. So B k j A j k, and since we are talking about this conjugate matrices, so they always commute. So what I can do, I can write it like this. So A j k and B k j, which is nothing but A B here is C will be C j j, which means these are the diagonal elements of the matrix C, and I am summing over all j. Okay. So this is nothing but the character of the matrix C. So thereby I can see the conjugate matrices will have the identical characters. Okay. So we'll stop here and we'll start again in the following class. Thank you very much for your attention.